how we generate a desired output from the given inputs. So I explain how a artificial neuron works, starting from the feed forward to generate an output and using the back propagation to optimize to change the weights until we get the desired output. So these iterations will keep happening until we see the expected output from this particular neuron. So that's how the artificial neuron works, right? Today, we will see programmatically how we can develop a artificial neuron, the perceptron. First, we would start with a simple example. Then we will go ahead and try to use Keras, which is one of the frameworks that is popular frameworks available for deep learning. And using the Keras, we will build a slightly more complex neural network. So with that, let's get started. I'll give you an overview of what we are going to build today. So we are going to build a neuron perceptron like this. There are going to be like 3 inputs. The inputs are x1, x2, and then the x3. So I'll place this as our neuron logic. In the neuron logic, let's say we have 2 things. One is the summation logic, and the other one is the activation function pi. Just give me a minute. Okay, let's continue. So we will be initializing 3 weights. So let's call them as W1, W2, and then W3. Any questions? Feel free to post them on the chat window. And then I'm going to introduce one more thing today, which is going to be called as the bias, and we would introduce a bias. So on the summation, this is what is going to happen, which is like sigma xi into wi plus bias. So that's going to be happening at this point. And let's call this as OL, the output of the left-hand side of it. And on the activation function phi, I'm going to use a sigmoid activation function. So this is going to be 1 by 1 plus e to the power of minus OL. So that would generate our output y. Okay. So for this perceptron, today we are going to write a program. Then the error part is so the error part E is going to be the difference between, let's say we call this as OR. So the output of this is OR. So the error part is Y, which is the original yi, minus yi hat. Your yi hat is nothing but your output of the activation function. So that is the OR. So this is the error part. And so what we have discussed is the feed forward, or also called as the forward prop. And later, after the first iteration, we realize what would be the error, and to reduce our error, we have to do the back prop. In the back prop, we are going to update our weights W1, W2, W3. Let's say at the first step, we would randomly initialize W1, W2, and W3. So let's call this as W1 at 0 iteration. So we would randomly give some values, complete the forward path, that means, and also bias. So I would introduce bias also, bias for the first iteration, 0, and complete this forward prop. Then estimate the error. What is the error of the forward prop that we have made? And using the back prop, we will try to find out the gradients of it. So what we need to find out? We need to find out dou E with respect to dou W1, dou E with respect to dou W2, and dou E with respect to dou W3. So these are the three that we have to find out, the three gradients. Once we found these three gradients, which we are going to do like this, dou E with respect to dou OR, output of the activation function, into dou OR divided by dou OL. So that is like output of the summation function, into dou OL divided by dou W1. So we are going to use this equation to find out the gradient of this, and same way dou E by dou OR into dou OR divided by dou OL into dou OL divided by dou W2. And third one, dou E divided by dou OR into dou OR divided by dou OL into dou OL divided by dou W2. Okay, so we need to find these three gradients. Once we have these three gradients, then for the next iteration, iteration number 2, W1 at 1, W2 at 1, W3 at 1. So we need to update the weights, right? So how we are going to update the weights? So that is W1 at iteration 0 minus the learning rate. We will also initialize the learning rate here. So let's say my learning rate is 0.1. I can choose my own learning rate, not a problem. Into, for updating the weight of W1, so we need to use the gradient dou E by dou W1, and for W2 at 0 minus eta times dou E divided by dou W2, and W3 at 0 minus eta times then dou E divided by dou W3. And we will put all of this in a loop because we don't know how many iterations we have to run. So we have to run as many iterations as possible till we get the expected output or we get closer to the expected output. So it might take 10 iterations, 20 iterations, 100 iterations, even 200 iterations. So we don't know how many iterations we are going to do that. So let's start with writing the program for all of this. Now comes the complexity, but don't worry. My intention of this exercise is to show you, okay, if you have to develop a single perceptron by yourself, raw from scratch, then you need to know all these things. Okay, first of all, what is E? So we need to find out these ones, right? So these gradients, not that somebody is going to do that gradient for us. We need to find out those gradients by ourselves, right? So let's find out those gradients. So what is E? So E can be represented in the form of, let's say, the original value, which is Y, minus the output that is generated, OR, right? So this is the E value. Now, if we try to derive this with respect to dou OR, okay, one more thing that I have to introduce here. The reason is we need to choose a cost function. And what is going to be the cost function? The cost function is not straightforward. This, let's say we choose the cost function as MSC, that is like mean squared error. Then what is our error? Error is summation. Let's say I is equal to, because we have many observations, I is equal to n, y minus the output which is generated by this, OR whole square. Okay, fine. Now, if we derive this dou E by dou OR, if we derive this equation, what happens? So this is going to be, let's say we use this chain rule to derive this, then this could be the loss of error. Let's call this as the loss of error here. So this is like 2 times y minus output. So that's like, think of this as x square. What is d by dx of x square? So we write this as 2x, right? Then again, we would be deriving this for this one, which is like y minus OR. So that would give us 1 by 2 of, okay, just a minute, because I'm trying to recollect how to do the derivative, because it's like quite some time I have applied the derivatives myself. So this would be like this, my mistake. So this is like 1 by 2 y minus the output on the right hand side square plus okay, now we are going to derive this. Why this 1 by 2? I'll explain in a little while. Okay, don't worry. The cost function that we are going to write is like this. E is equal to 1 by 2 of y minus OR whole square. We know y minus OR whole square. Y is our original value. OR is the output generated. So we are squaring that. And just that I am adding 1 by 2 over here. This is for faster optimization. Now we need to derive this. When we derive this, what happens? 1 by 2 into 2. So this 2 comes here. Y minus OR. So that's what I wrote here. But I just made a mistake in deriving that, plus again y minus OR. So and then when we derive this, it would be like 1, so which is going to be minus 1. Okay, so when we take this out, sorry, this is going to be minus 1 only. After a long time, I am trying to derive something. I forgot all the rules of the derivation. That's okay. So this is the derivative for x square, which is 2x. Then we are deriving for this, which is just the minus 1. So this is just going to be y minus OR minus 1. That's okay. So this is the derivative of this particular part. Similarly, we have to do the derivative of this one, the next one. What is the next one? The derivative of OR with respect to derivative of OL. And just straight away, let me write that. So that is going to be the cost function based one, which is like, what is OL? OL is nothing but, sorry, what is OR? OR is nothing but 1 by 1 plus e to the power of minus OL. So this is the OR value. So d by DOL of this entire equation. So this is like d by dx of 1 by 1 plus e to the power of minus x. I'm not going to derive this because okay, that's okay, fine. Let's try to derive this. This is generally given by 1 by 1 plus e to the power of minus x into 1 by 1 plus e to the power of minus x. So this is the derivative of 1 by 1 plus e to the power of minus x. So in same way, if we try to write this, so this is like OL into 1 minus OL. Why? What is OR? OR is 1 by 1 plus e to the power of minus OL, right? So 1 by 1 plus e to the power of minus OL. Sorry, this is OR into 1 minus OR. So this is going to be the second derivative. And the third derivative, so this is dou by dou E by dou OR, and this is dou E by dou OL. So we found out the two derivatives. And the third derivative is dou E by, sorry, not dou E, dou OL by dou W1. So what is dou OL? OL is W1 into X1. I am not writing the other ones because when we are deriving this for W1, the other ones are constant and the derivative of the constant is nothing but 0. So what is dou of OL divided by dou W1, which is nothing but your X1 itself. So these three derivatives, so to find out dou E by dou W1, we need to multiply this y minus OR minus 1 into OR into 1 minus OR into X1. So this is the final derivative. This is with respect to W1. And we need to write a program for this. Let's do that. And similarly, for the other two, dou E divided by dou W1 is equal to, again, y minus OR minus 1 into OR into 1 minus OR into X2. And dou E by dou W3 is equal to y minus OR minus 1 into OR 1 minus OR into X3. So by this, using this equation, we will find out these gradients. Once we found out these gradients, we can update these weights. Okay, fine. So let's do that in a program. In a program, it looks much more simpler than it actually looks like. So let's see how we can do that. So this is my input array. These are the inputs that we are creating. So let's write it. So what are the inputs that we are actually passing here? For example, first input that we are passing to the neural network is, let's say 0, 0, 1. And the remaining, 0, 1, 0. And the third one is, let's say 1, 0, 0. 1, 1, 0. 1, 1, 1. 0, 1, 1. 0, 1, 0. Okay. So these are the inputs that we are passing. These inputs are x1, x2, x3. And we have 7 observations here. So this is our input matrix. And similarly, we need to have y because it has to compare with y. And so that from this input, we have to generate that desired output y, 1, 0, 0, 1, 1, 0, 1. So 1, 0, 0, 1, 1, 0, 1. So this is the output that we have to generate. So we need to figure out how we can generate this output from this input. Okay, fine. So how many inputs we have? 3 inputs. Observations are 7, but inputs means the features. How many input features we have? 3 features, x1, x2, x3. How many weights we have to generate? 3 weights. The 3 weights that we want to generate is W1, W2, and W3. And adding a bias term here. So we would be adding a bias term, B. We will also randomly initiate the bias term. So we will be initiating 3 weights and we will be randomly initiating the bias term, B. Then in the forward computation, what will we do? We will multiply this matrix. So you would multiply this matrix, a matrix with x1, x2, x3 with the weights W1, W2, and W3. So this is a matrix. Now this matrix is 7 by 3, 7 rows by 3 columns. And this is a matrix with 3 by 1, 3 rows and 1 column. So we would get a matrix with 7 by 1. So this is like 7 by 1. And top of this, we would be adding the bias. So if we multiply these two matrices, so this is matrix A, which is the inputs, and these are the weights, W. So we will multiply A and W using a matrix multiplication. So we will get a new matrix. On top of this, we are adding a bias, and we are going to add the bias term to each of these outputs. So that is going to generate our output from this one. Then these values, let's say we call these values as OL. Now this is the matrix OL after adding the bias term. Okay. Now we are going to give OL. What is OL? OL is going to be a matrix of 7 by 1 to the activation function. So what is the activation function? Activation function is sigmoid. So that is going to be 1 by 1 plus e to the power of minus x. E to the power of minus OL. So for each input here, this will generate an output. So you would get another value. which is like 7 by 1. So for each input, we will get an output from this from this uh, from this perceptron. Okay, clear with this? Because it would always be confusing for people, like how this forward prop is happening. I'm going to repeat this. In my inputs, I have 3 input features, x1, x2, x3. And we have 7, what we have? We have 7 observations. So our input matrix is a 7 by 3 matrix. And we have to initialize weights W1, W2, W3. So we have initialized our weights W1, W2, W3, and converting this in a matrix form of 3 by 1. How does the matrix multiplication happen? Let's say first row with this column, second row with this column, third row with this column. And that's why when we multiply the matrix, these two matrices, we would get a new matrix with 7 rows and 1 column. On top of it, we are going to add the bias, and the output of this matrix, I am calling it as OL, and we are giving that OL to the activation function of OL, which is 1 by 1 plus e to the power of negative OL, and you would get your output. So this is your OR. Now clear with this forward prop? Let's write that forward prop first. So I created my input set, which is a matrix of size 7 by 3. My output is 7 by 1. This is the required output. This is the original output that we want. We will use it at the error term later. Okay. Now I need to initialize 3 weights, W1, W2, W3, right? So using the NumPy, and within NumPy, we have a function called as random. And using this, I am generating random values. Random values with the shape 3, 1. So this is a NumPy array. Weights is going to be a NumPy array now. NumPy array of the shape 3 rows and 1 column. Okay. And similarly, I am generating np.random. Using the random generator, another one only single element, that is bias. So this is how we are generating the bias, because bias term is going to be only one value, and we will add that value. This is called as scalar addition. We have one value and we add that value for every row in the matrix. If we do position by position, that is called as the vector addition. In scalar addition, we add this value to every element in the matrix. Okay, so that is why we are generating only one value, and you can see here our bias is just going to be one value. So we initialize the weights and giving the learning rate. Why do we need learning rate? Whenever we want to update the weights, we need learning rate, and I am initializing my learning rate to 0.05. Generally smaller the better, but here in this case, let's say we go with 0.05. After initializing the weights, I am printing the weights for you. So these are the 3 weights that we have generated. 0.37 W1, 0.95, which is W2, 0.7319, which is going to be W3. And the bias that we have initialized randomly is 0.59. The other day someone asked how we can initialize these weights. So this is random initialization is the best way of doing it, so that we do not have any sort of biasness into the weights initialization. Most of the times it is going to be a random initialization. So our weights are ready. Next is we need to create the functions. two functions that we are going to use here. Rest all of them are straightforward, but these two functions are important. First, we are defining, this is how we can define a custom function in Python. So this is defining a custom function. So we are naming the function as sigmoid. You can give any name for that, but here for easy understanding, we are naming the function as sigmoid. It takes one argument. Any function is a collection of arguments. So when we write a function, we need to keep in mind what all values are required to generate a output from that particular function. So here we are going to give only one input. So that is why only one argument. And it returns whatever the value of x, whatever be the value of x, it returns 1 by 1 plus this exponential is part of the package called numpy. So np dot exponential of minus x. So that is like 1 by 1 plus e to the power of minus x. So let's initiate this function. So if you want to test this function, we can test it. So sigmoid of 10. So what is the value of sigmoid of 10? It returns you a value of 0.9999. So remember, if you remember our sigmoid function is going to take values between, it can take values, any value, but the output is always going to be between 0 to 1. When the values are low, negative values, let's say we give sigmoid of minus 10, you would get 4.5 into 10 to the power of minus 5. So that's like 0.000 something. Okay. What is sigmoid of minus 1? 0.26. And what is sigmoid of 0? It should be 0.5, exactly 0.5, right? So what is sigmoid of 2? It should be some positive value, right? So it takes any input and it gives you an output between 0 and 1. And that's why the output of a sigmoid function is always treated as a probability. Okay. Then sigmoid derivative. Why we need sigmoid derivative? If you remember when we did manual derivation, so this is the sigmoid derivative of OR with respect to OL. And what is the derivative? OR into 1 minus OR. So this is the derivative of sigmoid function. So 1 by 1 plus e to the power of minus x. So if we derive this, what we get is, if we consider all of this as y, it is y into 1 minus y. So that is the derivative. So we are defining sigmoid derivative of x, whatever be the input, it returns, let's say, x into 1 minus x. Now, this is going to be useful for us whenever we are computing the derivative of the second component. First component is easy, y minus OR. You know what OR is. Second component is OR into 1 minus OR. And the third component is x1 itself. So when we try to compute this partial derivative, we just use y minus OR into OR into 1 minus OR into x1. So that is going to be the gradient with respect to W1. So that is why we are defining this function. For the first one, I don't need, even if we want to, we can. But what is the first derivative, dou E by dou OR? It is y minus OR. So this is like straightforward. And for the second, last one, what is the derivative of dou OL divided by dou W1? X1 itself. So there is no complexity in calculating it. Only complexity is in this. So that is why I am defining this function. Derivative of a sigmoid, I am naming it as sigmoid derivative, takes one input and it returns that input into 1 minus that input. So this is the derivative part. Okay, fine. So we have the derivative of sigmoid also defined. Not, this is not required. Let me delete these things. Here we are going to write a loop in which all these things going to happen, including the forward propagation as well as the backward propagation. So this is the forward propagation part and this is the backward propagation part. So that's going to happen inside this loop. Our inputs. What is inputs? Inputs is the input set which we have created. So what is the input set we have created? This one. So this is going to act as our input. First calculation. What is our first calculation? First calculation is this matrix. Inputs multiplied by weights. So this is the first calculation. So np dot dot. So this is a function which computes the dot product. Indirectly, it is the matrix multiplication. So matrix multiplication between inputs and the weights. So what it returns? So this function returns. Okay, let me show you as an example. So np dot dot of input underscore set. So what is our input underscore set? This one, which is a numpy array which we have created. And weights, what is the weights that we have generated? So these are the weights that we have generated. Okay, fine. Now let's see the output. So this is a 7 by 1 output. So this is a matrix of 7 by 1, 7 rows and 1 column. On top of this, we are going to add bias. So what is the bias that we have created? Bias is 0.59. So on top of it, we will add bias. Now, because we are adding bias, all these values will change. So you can see the values changes. So this is the matrix, which I am calling it as OL. So to compute OL, I am going to use this equation. We are calling this as XW, but that's okay. You can give any name. So if you want to convert this to OL, we can convert this to OL. So output on the left hand side. So this is, then the output on the left hand side, OL, we are giving that to the activation function. What is the activation function here we are using? Which is the sigmoid function. So we have defined the function sigmoid already. So we are passing that sigmoid to this OL. Okay. Now what it returns? It returns this one, which is another 7 by 1 matrix. Let's see that one also. OL output is this one, np dot this. So we have generated OL. OR, the output on the right hand side is sigmoid. We have already defined this function. So sigmoid of OL. So this is going to be a matrix of order 7 by 1. So we have got a matrix of order 7 by 1. So we have generated our first iteration. Okay, so we have completed our first cycle of feed forward. So this is how we computed the output of the left hand side of the neuron. So this is how we computed the output of the left hand side, and the output on the left hand side is passed to the activation function, and from that we generated the output on the right hand side. And the output on the right hand side is nothing but our output for the first iteration. So we got this and we are calling this as OR. Okay, let's call this as OR so that when you read this code, you understand what OR. Now, what is our error? Error is OR minus the labels. So this is our error. And we want to print the sum of the error. In fact, if we square them out, then that would be even that would be better, but we are not summing it out. Sorry, we are not squaring it out. We are directly summing it. That's okay. It's still fine. So the first derivative, what is the first derivative? Let's call the first derivative dou E by dou R, and I am naming it as d cost. Just a minute, I lost my pen. Here it is. Okay. So let me show you. So dou E by dou OR, and we are calling this as d cost. D cost is nothing but we are taking the difference between y minus OR. So this is my first derivative. The second derivative is dou OR divided by dou OL, which we are calling as dpred. So what is this dpred? Dpred is equal to sigmoid derivative. So sigmoid derivative. So the second one is sigmoid derivative. What is sigmoid derivative? OR into 1 minus OR. So that is the sigmoid derivative. And finally, the derivative with respect to the derivative with respect to your inputs, right? So the derivative with respect to your inputs is inputs itself. Why it is inputs itself? Sorry, derivative with respect to weights, dou W1 x1 divided by dou W1, rest all of them are constants. So if we derive this, we would get x1. So which is going to be x1 itself. So we are going to multiply these two, which is x1. So this is for your computation of the gradient. So that's what we are defining here. Okay. D cost is equal to error. If we have squared it, we would have got 1 by 2 into something minus 1. But since we are not squaring this, we are calculating this as error itself. So this is your first derivative. Second derivative, we have already defined this function. That function is named as sigmoid derivative. So I'm using the sigmoid derivative. So sigmoid derivative of OR, not Z. So this should be OR, rename it to OR. And the derivative of these two is multiplied d cost into dpred inputs. So we have the inputs which we have to multiply again, right? So inputs, we are giving the inputs in the form of vectors, right? So we need to transpose that. So we need to transpose that. And now when we compute the new weights, weights is equal to minus the initial weights. What were the weights before? Minus learning rate times into np dot dot. This is going to generate the dot product between the inputs and the derivatives that we have for each of those observations. So that way we would get this. So this is the gradient descent. Someone asked, which gradient descent? You do not have to really use any of the gradient descents. We can write the gradient descent function as simple as that, right? So learning rate times multiplied by your gradient. And how do we compute the gradient? So here we have compute the gradient only up to first two, that is with respect to the error and with respect to the OR, and we need to multiply this with respect to W1. So for that multiplication, we are performing a matrix multiplication here. So our weights will get updated, and our weights will get updated in a way it will try to reduce the overall error, and we will run this loop for, let's say, 200 iterations here and see how much our error decrease. Okay. And we need to also update the bias. So we are updating the bias minus. For bias, there is no need of derivative. We are just using these values itself minus learning rate times the same number. So because this is bias is a constant, even when we try to derive, it would not make much of a difference. So we are just updating the bias with the help of the same derivatives, which is dcast and dpred. So that is why the learning rate times of dcast into dpred. And this implements both the forward propagation. So till this point, it is forward propagation. So here we are computing the first matrix and passing that first matrix to sigmoid to generate the outputs. And here we are passing the back propagation. So we are computing the derivatives and we are updating the weights. And when we run this in a loop, one iteration by one iteration, one iteration by one iteration, our error would start to decrease. And that is why after every forward prop, I am printing the error so that we can notice how our error is decreasing. So now let me run this loop. It ran already. It's very fast. 200 iterations is not a big deal. It starts with 1.88 and you can see after 200 iterations, our error has almost decreased to 0.11. We can still decrease this further. So there is a possibility. Let's say we increase the number of iterations to 300. We keep a watch on how our iterations are decreasing. So now it might have got reduced even further, something like 0.08. If we try to loop it over for more number of iterations, the error would keep decreasing. It would reach a point where it trying to reiterate anything further not going to decrease, then we would say, hey, we reached the least value of error and we would stop there. Now we have our model ready. So we have our I would not say model, but we have our weights ready. What is our perceptron? Our perceptron is nothing but the weights, right? Now what is our final weights? Let's see the final weights. Let me print the final weights for us. So my final weights are this. Compare these weights with the original weights where we have initiated them. When we initiated them randomly, our weights are 0.37, 0.95 and 0.73. But what were the weights we got after 300 iteration? 0.62, 2.9 minus 1.79. So these weights are the ones that are giving us that are going to give us the least error for the training data that we have given. And these are the weights that we were actually learning for. Why we were training the perceptron? We were training the perceptron to generate the desired output from the inputs that we are giving, and through these weights it is able to generate the desired output from the input. And also let us look at the bias value. The bias value when it was initiated at the first step was 0.55. Now it is roughly around minus 1.23. So these values are the ones which can give us better decisions going forward. And we learned these values by iterating over the data slowly. And final values that we have received is bias term is minus 1.2 and the weights W1, W2, W3 are these. Okay, how can we use this? These weights are nothing but our model. This is what when we say we have generated a model. What is a model? A model is nothing but this mathematical formula that creates your output from your input and keeps it very close to your desired output. Now we have the weights, and if we have to find out what would be the output for a given input. So I am creating an input here. How many inputs are required to our model? 3 inputs, x1, x2, x3. So these are the 3 inputs that I am giving, 1, 0, and 0. And how do we generate an output from this? Forward propagation. Remember the forward propagation? So to generate the output, first we need to multiply this. Right now we have only one observation. That observation is 1, 0, 0. And we need to multiply this 1, 0, 0 with the weights. What were the weights? 0.6. So this is 0.6. This is 2.9. This is minus 1 point, what was the value? Sorry, minus 1.79. So when we multiply these two, we will get an output. On this, we are going to add the bias. What is the bias value that we have? When the bias value that we have is minus 1.23. So this is minus 1.23. And you would get an output in the form of this. Again, you would have, you would get, so this is 1 by 3, and this is 3 by 1. So you would get a matrix which is 1 by 1. My mistake. So we would not get this. Sorry. So we would get a 1 by 1 matrix, which is just going to be one single value. And then we would pass this value. This is the output of the left hand side, right? Summation. And we pass this to our sigmoid function. So sigmoid of OL will generate our output on the OR side. So this is going to be our final output. And that's what I have written the code for here. So we pass this as the input array. Now the dot product between the weights. So let me show you separately, not a problem. So np dot of your array. So which is just going to be, let me define that array here. This is my input values of x1, x2, x3. And I need to compute my output, right? Output on the left hand side is equal to np dot of single underscore pt comma weights, our final weights, not the initial weights. These are the weights that we are going to use to compute. Okay, so it would give us a value, and let's print that value. OL is 0.620. So what is the OL value? Sorry, not OL. So this is 0.620, this value. And to this, I have to add the bias term. So let's add the bias term, OL plus the bias. So this will be the output. Sorry, this is not the OL. This is the weight matrix, right? So let's call this as W. Now W plus bias is your OL. So this is the output generated. And let's look at this value. So our OL value is minus 0.6. So what was the value of OL? Our value of OL is minus 0.6. When we multiply this with this column matrix and add the scalar, we got minus 0.6. Now, this is the output on this side. We need to apply sigmoid on top of it, right? Now let's apply the sigmoid on top of it. So sigmoid of OL, that is going to be our OR, output on the right hand side. And let's see the OR value. So OR is 0.35. So the output that we have generated is for this input data, which is going to be like this. This is going to be 0.35. Now, how do you interpret this 0.35? Think of this as a probability. If the inputs are 100, then the output probability that it is going to be 1 is 0.35. When it is close to 1, that means our output is going to be 1. When it is close to 0, our output is going to be 0. So we use a cutoff. Now think of this as cutoff. Cutoff is 0.5. When OR is less than 0.5, then our prediction y hat is equal to 0. When OR is greater than or equal to 0.5, our prediction y hat is equal to 1. So this is very common. That's why I said you need to understand some of the concepts of machine learning. This is how we do use the probabilities in machine learning. When the probability of something is less than 0.5, we will consider them into 0 predictions. When the probability of something is greater than 1, we will consider them into 1 prediction. And finally, we are able to completely program a single perceptron. This is just a single perceptron in Python. So now I can use this perceptron code to train any model for that matter. But remember, the only caveat here is we assumed that the activation function is sigmoid, and this code is only valid for a perceptron if and only if the activation function is a sigmoid. If we don't use, if we want to use some other activation function like tan h, the derivative that we have used in the second part in the derivatives of the chain rule, the derivative that we have used is the derivative of a sigmoid function. So if we think that we want to use tan h or ReLU or something else, then we need to replace this derivative also. So in the derivative, instead of calling this as a sigmoid function, even for the forward propagation, in the forward propagation, we are applying the sigmoid function on this. So if you want to use something else, like if you want to use tan h, then you should create your function like this. Let's say I will create that function for you. Define tan h. It takes one input, so tan h of x. Return np dot exponential of e to the power of minus x. So this is minus x minus np dot exponential of x. So that's the numerator. So let me write that so that people are not confused. So if I have to use the tan h activation function, so let me write it somewhere here. Tan h of x is equal to e to the power of minus x, e to the power of x. Oh, sorry, this is how it is. E to the power of x minus e to the power of minus x, right? So this is the tan h equation. So this is, we are going to write a function for this tan h equation. So this is plus x and this is minus x. So which completed the numerator part. And similarly, we have to do the denominator. Denominator is np dot, so this is plus x. So np dot exponential of x plus np dot exponential of minus x. So this is the tan h function. Now we need to replace the sigmoid of OL with tan h of OL. This will not change. Summation function will remain the same. We need to replace this sigmoid with this newly created function, the tan h. Let's see how does it work. Tan h of 10. What is the value it is going to generate? 0.99. So it's close to 1. Then tan h of minus 1. Sorry, minus 10. let's say this is close to minus 0.99. If you remember the concept that I discussed yesterday, tan H is also like sigmoid, just that your output is going to be between -1 to +1. Sigmoid output is always going to be between 0 to 1. Tan H output is always going to be between -1 to +1. That's why for a negative value, for a high negative value, we are getting -0.99. For a high positive value, we are getting 0.99. So our output is always going to be between -1 and +1. So now we would replace this function, so this function here with the tan H function, and similarly the derivative of the second part, that is derivative of OR with respect to OL, should also change. So this derivative is the derivative of sigmoid. This is not good for tan H. Now we need to find the derivative of tan H. It would be difficult for me to derivate it, because even I don't remember all the rules of the derivatives now. So we need to derivate that and find out the derivative of tan H and replace this function with the derivative of the tan H. So that is why we need to pay a little attention to how all these functions and how all these things are being programmed. Imagine if doing a simple program of one perceptron with one activation function requires so much effort from us. Then if we have to build a complex multi-layer perceptron, what example that we have used is a simple one single perceptron, and to program that single perceptron, I had to create the sigmoid function. I had to find out the derivatives of all the output, from output to OR, from OR to OL, and then from OL to W, and do this. If we have many inputs and then we have a network of hidden layers to generate an output. So initialization, first of all, itself is a very big task. So how many weights we have to initialize here? So the number of weights that we have to initialize here is, this is 1, 2, 1, 2, 3, 4, 5, 6, 6, and this is 1, 2, 3, 4, 6 by 4. So we say np dot random dot rand of 6 by 4. So this initialization, just initialization. Then from this to this is for the second layer. So this is 4 by 2. So here we need to again set of weights to np dot random dot rand of how many we need to generate? 4, 2. That is 4 rows and 2. Right. And from this to this, which is going to be like 2 by 1. So we need to initialize two weights here. So np dot random dot rand of 2, 1. So this is at the initialization part. Then the matrix multiplication. So np dot dot of your inputs, comma, weights plus bias. We need to add a bias, and now we need to add a bias at each layer. So this is the bias for the first layer. This is the bias for the second layer. So this is B1, this is B2. So this is, let's say, B1. So this will generate this output. Let us call this as H1 layer. So you would get a vector. What would be the vector that you get here? 6 by 4, 4 by 2. So that would be a vector of, matrix of size 6 by 2. So that is your H1. Then you multiply this H1, which is a 6 by 2, by another matrix, which is going to be like 2 by 1. So 6 by 2 by 2 by 1. So you would get 6 by 1. So that's like another matrix that you would get here. And then finally, you would map this as your output. Of course, the bias term will always be there. The programming part will be more and more complex, and it's not so easy for anybody to write the program from scratch for everything. Here I might use sigmoid activation function, and in these hidden layers, I might use a ReLU based activation function. So when I am finding the derivative to do the backprop, first from here to here, it is error with respect to the output of hidden layer 2. This is straightforward because we are directly linking with error. So this was nothing but your y minus your h1, and this is y minus your h2. So this derivative is not a problem. But from here to here, there is a sigmoid function, activation function here. So we need to do the sigmoid derivative. Here, if we have ReLU, then from here to here, we need to do the ReLU derivative. And finally, from this, we will get the two weights W11, W12, so on. So easy to make any mistake, easy to make. Even a very seasoned programmer would get confused with so many things. This is where those frameworks like TensorFlow, Keras are going to help us in creating all these complex networks, programming these complex networks with easy to use methods, with easy to use functions. So that's the beauty of TensorFlow, Keras, PyTorch, Caffeine, or whatever it is. When we do the same thing with the help of Keras, you would see how simple and how easy it is to generate a program for such a complex neural network. But because people have asked about it, like they want to see how the gradient happens, how the gradient descent works, and how the weights initialization happen, everything, I have shown that with a simple example of writing the code for one single perceptron. If I have to write it for a multi-layer perceptron like this, probably I would take a day or even more than that, a couple of days to do that. But I would never do that because I would always go with the frameworks like Keras, TensorFlow, etc. to do that job for me. It would make my life much more simpler and easier. Okay. Any application can be developed using AI, but given that you have a predefined desired output and you have some inputs to generate that output. So don't think of AI as something like magical. So it's don't say that, okay, hey AI, can you give me the vaccine for COVID, or can you give me the solution how to prepare the vaccine for COVID? This is not, AI is not God to altogether try to find out magically what would be the formulation of vaccine for COVID, right? So there is no way that it can generate a output something like that. When can it generate an output? It can generate an output if it is trained. Like if someone asked me a question in a language that I never heard in my life, first of all, will I be able to understand that question? Will I be able to answer that question? No way, right? First, we need to train it to do something. Once we train it, it is definitely capable of doing that job millions of times. Why we are going with AI? We are not going with AI because AI is smarter than human intelligence. Now, no AI is smarter than human intelligence, at least not yet. Our human brain is capable of finding very, very complex patterns, even with images or with text data, which AI will always struggle to find out. If that was the case, why Google Translator has to be so pathetic? Try to give a very complex Telugu sentence or Sanskrit sentence or a Tamil sentence to Google, ask it to translate. It will, but the grammar, everything is broken into pieces. If Google's AI is so efficient, why is it struggling to translate a simple sentence from, let's say, Sanskrit to English, or Tamil to English, or Telugu to English? The reason is, it all depends upon how well it has been trained. If it has been trained well, then of course it can do a better job. It can do as good as a job like someone who knows that particular language. Now, the next natural question that comes to our mind is, when AI is not intelligent than us, then why are we going with AI? What is the need for AI? Right? So this is a common question that I face every time when I go to any talks or workshops. I hear people thinking that, hey, AI is smarter, AI is that, AI is this, AI can do anything magical. Then I try to completely shatter their thoughts, saying that, hey, wait, AI is still not yet intelligent than a human being, not more intelligent than a human brain. And a lot of people looked at me and said, like, what is this? We are not expecting this. They think that AI is many times better, many times smarter than human intelligence. That's a common mistake that we do. No way. Then what is the reason why we are going with AI? The reason why we are going with AI is for two things. One, scale. If we ask a person to take each and every decision, it's practically impossible, right? For example, let's take the trading example that I was speaking about. There are probably, let's say, 5,000 stocks. I'm just giving a rough number. 5,000 stocks that are being traded every day on, let's say, National Stock Exchange. Now, is it possible for a human being to watch each and every stock and make decisions on whether to buy that stock or not? No. Now, if for that matter, if someone has to do stock trading, what would they do? They would select, let's say, 10, 20 stocks. They observe that stocks over a period of time. They get much more knowledge about these stocks, and they will stick to trading only on those stocks. Unless they do some research, they would not risk to put that money into a stock which they have never researched before, which they have no knowledge about. Now, if we can build algorithms which can try to learn much faster than human being, because computers are way faster in processing than us, but not smarter than us. So let us use that processing power of the computer so they can do the processing faster. That means they can learn faster than us. Now I have a mechanism to even monitor all the 5,000 stocks, and AI will tell me, hey, these are the stocks which are trending well. These are the stocks you probably have to look into. Now, when I had to do it individually on my own, yes, my human brain is more intelligent, but I have the limitations of processing. We will not be able to process as fast as a computer. We will not be able to learn as fast as a computer. Just think of it. All these calculations that I have shown on this page, for 200 iterations. I did not made AI intelligent. It is my intelligence which built this perceptron. I tried with one iteration, and with one iteration, I have derived something, I have built all of this. Now I let the AI to learn from it. It performed those 200 iterations in a matter of a split second. So if I had to do those 200 iterations by myself, I would have at least taken a week's time to complete those 200 iterations. So that's the processing power of computers. And that's what we are leveraging here. Not that because they are smarter than us. Second thing, one is scale. Now, through AI, I can try to monitor all the 5,000 of them. Second one is the amount of information we can process. I can process one image at a time. I can process two images at a time. Maybe I can also process 10 images at a time. But if we have to do something on, let's say, 1,000 images at a time, unfortunately, our human brain is not built for such type of applications, not built for such type of processing. Then you definitely need to make use of a computer. Like, for example, there is 1,000 CCTV footages being live recorded across the city, and the police control room want to monitor them all at a time. Now, what should the police control room should do? Put a TV for all the 1,000 videos that are being live streamed, and ask a police person to sit in front of it and monitor them for any kind of things which is unwanted. Is it possible? Is it scalable? No. Now we can try to leverage AI. Like, for example, there would be let's say 20 screens in the control room. Every footage is being captured and recorded, and AI will try to process them in a matter of a split second. Every frame, every second, 24 frames are being recorded, right? In a video, all these frames can be processed just in a blink of a second, and only those frames which has something that we are expecting, like some disturbance or some event that is happening, then those frames has to be triggered onto the TV, where humans can watch and see, hey, let's look into this, something happening there, right? So that's the power of AI. Don't think that we can do anything with AI. No, not yet. AI is not there. So the intelligence is two types. One is called as the specific intelligence. The other one is called as the generic intelligence. Humans are very good at generic intelligence. Like, when you are shown something, you learn it, and you can apply that knowledge in so many different instances of it. But machines are not that good yet. Machines are good at specific intelligence. What is specific intelligence? You help them to perform a task, they are capable of doing it millions of times, many times faster than you. But if you try to ask it to generalize to something else, no, it would not be able to. For example, if you have seen, let's say we show a kid the picture of a tiger. Now, the kid knows how a tiger looks like. In the next instance, I will try to show the picture of a leopard. The kid has never seen a leopard. I have only told him that this is a tiger. Now, when you show a leopard to him, maybe he will not, or she will not be able to call that animal as a leopard, but he or she can recognize that, hey, this is closer to a tiger family. The features of it is very closer to a tiger family, and she will probably, or he or she will be answering it as a tiger. In a way, that is good. That is intelligence. That's the human intelligence that we are talking about. But a machine would say, hey, this is not a tiger, and it would not be able to generalize and say, hey, this is very closer to a tiger. This is probably an animal that belongs to a tiger family. That general intelligence is not possible. If you show the picture of a tiger, it will say tiger. It will, otherwise it would not, it would say not a tiger. Show it a leopard, show a lion, it would simply say, no, this is not a tiger. That's what I was told you. No, sorry, that's what I was trained on. When you show a picture of a tiger, I will say it is a tiger. Otherwise, it's not my business. I would keep on saying it's not a tiger. I would not try to generalize my intelligence. Okay. So AI is not yet there where it can demonstrate that generalized intelligence. It is still being exhibiting specific intelligence. You tell it how to learn for a particular task, it can learn and it can perform the task millions of times, scale and faster than us. That's the reason why we are going to AI. Okay. I hope that answers your question. Fine. We will see the framework tomorrow and a complex example with the Keras framework tomorrow. Now I am open for questions.